And okay, Kevin, you have to let me know. Can you still see the presentation?
Yes.
Okay, cool. Okay, just let us know if you can't see the presentation or hear us.
Okay, will do.
Is that a good deal?
Yep.
Okay. Good morning, everyone. We are this summer's 2025 REU tech team, focusing on water quality in the Yucatan Peninsula.
And we'll be using tech to understand bathymetry and groundwater flow in Holbox cenotes.
My name is Marisol. I'm an ESRM Environmental Science and Resource Management major at Cal State University, Channel Islands.
And I'm Kat. I am a geology student at Cal Poly Humboldt, and we'd like to thank Dr. Megan Brown and Dr. Melissa Linchesky for being our mentors.
So presentation overview, we will be covering the backgrounds of the Yucatan Peninsula geology and also the instruments being used for our research. We're also going to cover why this topic matters, and then we'll go into each of our proposals.
So to start with the Yucatan Peninsula geology, the Yucatan Peninsula is relatively flat and primarily composed of porous limestone. This limestone is heavily dissolved and eroded over time by slightly acidic water, which forms karst. And this karst, it features cenotes and fractures. And as a review, cenotes are natural sinkholes that expose the groundwater table when the ground collapses. And when coastal cenotes are deep enough, fresh water meets saline water, which forms the boundary called halocline. The Holbox fracture zone is a network of cracks that run parallel to the coast in northeastern Yucatan. And these fractures create really complex paths, which influences how groundwater moves. And then these are just some figures to the left. This is the regional ground flow in the Yucatan Peninsula. And then to the right, this is the Holbox fracture zone, where you can see Puerto Morelos and Cancun on the map.
Okay, going into the background of the instruments we'll be using, there's going to be 5 different devices that we'll be focusing on. The first one is going to be sonar, which is a technology that uses sound waves to detect objects, measuring distance, and map underwater environments. 2 sonar equipments that we're going to be using are called the Aquadop and Chirp. The Aquadop is going to be measuring the water flow velocity in various aquatic environments using the Doppler effect. Chirp, which is our second sonar device, measures the bathymetry of underwater environments. We're also going to be using Geode, which is an advanced GPS technology. It's just going to take accurate coordinates of our locations. And then we'll be using a hydrolab, which measures water quality by recording temperature, pH, conductivity, and turbidity. And here are some figures of each of the devices we'll be using. This one right here is the Aquadop. You can see the sensors right here at the end, which will be using the sonar. This right here is the hydrolab, and it's connected to a handheld device, and it's easily portable, so we can take it into the cenotes and it's waterproof. This right here is the Chirp, and we're going to be using a field phone that has the Fish Finders app to collect the live data from the Chirp. And then this is the GPS Geode. It's a small kind of box that I'll be carrying around with me with the fish finder, just to have like secure GPS coordinates.
So to go into why our topic is important, it's more than just measuring the velocity or bathymetry of groundwater. Groundwater is the region's primary freshwater source. So if we're able to understand how it moves and how it works, we can inform scientists, biologists, and local communities about conservation and management practices. There's also a lot of gaps in existing research. So if we're able to conduct our own research, we can understand the region a bit better. And also CHIRP is an inexpensive method to measure bathymetry, which allows accessibility for scientific research.
Okay, we'll now be going into our individual research questions. So mine, I will be doing understanding the depths of cenotes, using chirp fish finders to measure the first order bathymetry in cenotes. Okay, so some background. This is my second year in environmental science, and this is the first time I've ever heard this funny little word called bathymetry. I don't know if I'm gonna learn to love or hate it towards the end of the summer, bathymetry, I don't know. But it is a study of the depth and profiling of bodies of water such as rivers, oceans, and in this case, cenotes. Understanding the depth is a key component to understanding the water dynamics of the water flow, sediment deposition, and the formation of underwater features in the cenotes. These features include caves, river passages, and haloclines. And then right here, this figure, I found this cool bathymetry map of Lake Michigan. And as you can see, the different contours and depths within the lake. Some parts are deeper than others. And it's just a cool visualization to see where the deepest parts of any bodies of water is. Okay, so a background on my main device, which will be the CHIRP, the fish finder. CHIRP stands for Compressed High Intensity Radar Pulse. This is mostly used by fishermen to detect fish and map underwater terrains. The fish finder has three main degree settings, which are 7th degree, 20, and I believe the 45 degree. This is also a sonar device, a sound navigation and ranging device. We'll be using a sonar from the CC to test for ground truthing for the fish finders. And then right here, you can see how different sound waves bounce off the floor and then bounce back to the chirp. That's how we get our data. So my hypothesis for this research, chirp-based fish finders will be able to penetrate past the halocline layer in cenotes. However, the depth profile may decrease accuracy due to wave interferences. So we know that fish finders can be used in salt and fresh water since they're detecting fish and stuff. But I just want to know if the depth of cenotes can accurately be portrayed with the fish finder. My research question, how does the presence of a halocline affect the accuracy of chirp fish finder sonar in measuring the bathymetry of cenotes? For my methods, I have 3 sites. I'm going to be testing Yamkin with a halocline layer. So this is our deepest cenote at about 100 meters, which includes a freshwater halocline layer and saltwater. It has relatively low tourism, which is an important thing to note. My second site will be LL, La Laguna, which doesn't have a halocline layer. This is all fresh water, and it's right next to the YK cenote, making it a great site and convenient site for my question. My third will be a control group, a community pool, to test the efficiency of the equipment. So for my equipment, fish finders, I'll be using 3 new ones and 1 previously used by Megan and Laura on past REU research. I'm going to be using the 7th degree narrow feature and then the 20 degree narrow feature just to get different range in data. I'll also be using the geode to assist with the fish finder. Right here in this picture, you could see that the geode is in the container just because it's not waterproof. You need to keep that safe. And then the chirp will be on the side, hanging off the little board. I'm also going to be using the HydroLab just to measure the temperature, salinity, and conductivity and turbidity of the water, just so I know what the water is when I'm dealing with it, like what's in it, what I should look out for. sonar, like I said, we'll be using we'll be introduced to a sonar piece of equipment at CC, so we'll get to learn it there, but I'll be using it for ground truthing. And then our field phone. So procedures. I will be replicating previous methods, which include swimming in cenotes in a grid-like manner. So we'll be swimming with the board, the chirp, and then the GPS, just going back and forth, just trying to get everything we could and make sure that the chirp is right, is getting the data right. A new method I want to try is using a small inflatable raft to gather data. So instead of being actually in the water and kind of interfering with some movement that the chirp can be detecting. Well, it's originally used for fishermen, so they're on boats. So I think it'd be a good idea just to have a little raft and like just paddle around the cenote. I'm gonna be repeating this procedure 2 to 3 times per degree, so the 7th and the 20th degree for each cenote. Okay, so my potential limitations. If cenote has high turbidity, which is just cloudy water and particles in the water, the chirp signal can be scattered or absorbed by particles in the water, which can result in unclear data. Geological features like cenotes, like rocks, caves, or fractures can cause sonar signal to reflect off objects in unexpected ways. So if there's a big rock on the very bottom of the cenote, I won't know if that's like the true depth. So that's some kind of limitation. Water temperature and density variation can affect how the sound waves change the measurements of the chirp. So just knowing what's down there can change the wavelength. Oh, okay. And this is my last slide. I'm going to go ahead and pass it on to my partner.
Okay, thank you, Marisol. I'm going to be going over groundwater flow dynamics and the role of haloclines. So my proposed research question is, what influence does the presence of a halocline have on the groundwater flow in Hopash cenotes? And my hypothesis is that although the velocity might be influenced by the presence of fractures, the flow in cenotes with haloclines will likely have a slower velocity due to an increased amount of density and salinity. I also think that flow direction below the halocline may be different from the flow direction above, since saline water is being pulled through fractures. So the first step in conducting this research is to find my locations, site selection. I need a site with a halocline and I need a site without one. So I'm also going to be looking at Yumkin, the 100-meter deep cenote with a halocline, which is indicative of saltwater intrusion. And you can see in this figure on the right side that this is pretty accurate to what it would look like. It's got that halocline layer and it's got the saltwater intrusion. La Laguna is a freshwater site that's shallower. So it would only come up to, the freshwater layer. Both are in proximity to each other, and they are both located in the Hopash fracture zone, which means that they share structural and geological characteristics, which makes them good cenotes for this research. And this is a Google Earth image that shows how close they are to each other. This is La Laguna, and this is Yumkin. So step 2 is collecting data. This is what I think is best. So I'll be working with Marisol with the chirp and sonar to map the bathymetry of Yumkin and La Laguna, because we have to confidently know where the floor of the cenote is at all test locations to avoid any error. So we don't know if the device is hitting the ground or not, unless we use the instruments. So we'll be using Dr. Brown and the previous NIU students' method, as Marisol explained, snaking around the cenote, and doing vertical motions as well to get a good map. The second step is using the aqueduct that Dr. Lanchesky's previous master student, Laura did, where we have a rope at the field site with every 2 meters marked, where these measurements can be recorded. The aqueduct will stay vertical with a buoy, and we'll just take measurements around this perimeter and ensure that the GPS locations of all 8 sites are recorded. And then we'll be using the hydrolab every 2 meters in depth to record temperature, salinity, and conductivity to make sure we know exactly where the halocline is. We also I might have to redo this a couple times to make sure I have a really accurate profile. And we'll be using software to organize and interpret data. So potential limitations, according to Laura's thesis, fractures create really complex underground paths, which influences how groundwater moves. So it would be difficult to distinguish whether the flow velocity is caused by the halocline, the salt water, or if it's because of the fractures. The zone, the Holbox fracture zone, is really complex and it's still being studied. So it's a challenge. As Marisol mentioned, data collection near the edges of the cenotes might be inconclusive because of the blockage, because it's using sonar to bounce off of nearby objects. And also, because Yumkin has that saltwater intrusion, understanding how the tide works may also affect this data. And to reiterate, our research projects are more than just water. We are doing these projects to understand how the water moves and to map the bathymetry, because we can understand how these contaminants and chemicals are being transported. So if we're able to understand how it moves, then we can understand and apply this knowledge. And we can also fill more gaps in research. And that's it. Thank you very much.
Any questions?
For the hydrolab, are you able to fully submerge that up in the water? Like it's going to go down and then they set it up. I might think it's like this surface.
Yeah, it works both in and out of, like, you can have a fully submerged one. So it's, as long as it's vertical, then you can take accurate measurements.
And it has different little prompts in the bottom, so that the different prompts, like, it is what, it's like the temperature.
One of the other things that I just want to remind that I haven't said anything about was the chirps. One of the things we did find is that we need to get a local SIM card.
Yes.
So, we need to go and get that right away. And the reason we want a local SIM card is because a local SIM card will know which
It'll be better for GPS.
So we need to do that right away.
Yeah.
We have to be able to go. SIM card. And the airport, well,
Any other questions?
no, thank you. I have all your documents. Okay, cool. I didn't know who was that. There we go. Okay.
Is it okay if I just open up your email?
Yeah.
Okay.
Yes, Dutch. This is the percent of the Canton REU.
No. It's okay. I can just present the PDF and then I can have my notes.
Come on in.
I don't think there's a way to put this into full screen. So we're just gonna scroll through it. Okay, good morning, everyone. My name is Laura Lee Granados. I am a marine bio student at the University of the Virgin Islands. And today my project proposal is quantifying macro and microplastic pollution in cenotes, a correlative analysis and chirp-based detection accuracy. So just a quick outline of the presentation. We're going to go through some background and information of the project. We're going to connect macro and microplastics together. We're going to have an introduction to chirp and sonar and how it specifically relates to my project in addition to what the last presentation talked about. We're also going to look at my research questions and my objectives, my study method, my predicted outcomes, and some acknowledgements. So before we get started, plastic is everywhere. Like it is in everything, it is everywhere. Worldwide, we are producing over 450 million tons per year. Plastic in and of itself has various different applications. You know, it's cheap, it's readily available. You can use it and toss it, and it really fits this like busy lifestyle that we live in these major well-developed countries, right? We're go, go, go in the city. Everyone is busy. Another really good benefit of it is it's used a lot in the medical field because it's sterile, right? It's really important that we keep that sterile environment when we're going through surgeries and things like that. So it's just really easy to just grab it and not think about it ever again. However, 20% of this plastic actually ends up in the environment, so it isn't properly recycled. It doesn't get properly disposed of, and then because we use it and we don't even think about it again, it's just ending up out in places it shouldn't be. Most of our plastics aren't biodegradable and they don't decompose. So basically what that means is instead of breaking down to these like basic compounds, like you think like a leaf would, when it falls down, it breaks back and it goes back into the ecosystem, plastic just degrades. So it breaks up into smaller and smaller and smaller pieces and it never goes away. So what's the big deal about this? Like, why does it matter that it's not going away and it's sticking around? It poses a risk to our fisheries and tourism. For those of you who don't know, fisheries are a really, really big part of our worldwide economy. And it's this really, really complicated system that has a lot of international trade and stuff related to it. So if our fisheries start to decline, there's a lot of like other things that are going to be affected by this, including international relationships. It also affects our tourism. So we like to travel, we like to go on vacation, especially out in like other places. They have more of this system where vacations are encouraged, unlike here in the US where it's work, 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 right? So if tourism starts to go down, obviously that is also going to affect not just our economy, but the worldwide economy. Plastics also contain and transport harmful chemicals like BPAs, phthalates, PFAs, and etc. This is important because these different types of chemicals can increase our human health risks. So things like cancer, they can affect fetal development, they can affect fertility, amongst many other things. They can also imitate our personal hormones, right? So it can affect our growth and our development. Monitoring plastic is a really, really, really hard thing to do. It takes a lot of time, it takes a lot of labor, and it takes a lot more technical support once it starts to break down. Because think about it, it's really hard to categorize something that's really, really small compared to something that's really big that you can physically see and hold. So microplastics are going to be those plastic pieces that are less than 5 millimeters. They can be primary microplastics, meaning that they were made and manufactured that way. Or we can get secondary microplastics because as I mentioned, plastic just breaks down, right? It doesn't go away. It's always here. It just breaks down. So those bigger pieces are going to turn into the smaller pieces, which are starting to cause a lot of problems for us. So if we're able to find a correlation between the large plastic sizes that are starting to break down and make more of these small plastic sizes, this could possibly be used to try and make it easier to monitor the smaller plastic pieces. Okay. But there's also a problem with just trying to look at the big pieces, right? So how many people have done like a citizen scientist project where they've gone and they've like done like a beach cleanup or like a wetlands cleanup or something of that sort, and they give you the data sheet and you're filling it out as you're going, right? If you're looking and you're categorizing these materials, when we're looking at the water column, we're mainly just looking at the surface level, right? Because again, if you're trying to look below and you're trying to look into the water column, it gets really hard and it gets really difficult because you can't physically see that with your eyes, right? You would have to go down and look at it, and then it's really hard to have the skills and the abilities to go down into the water column. to categorize and look at what is actually down in there. Okay, so mainly if we're going to try to look at big plastics to try and see if there's a connection to little plastics, we're only going to be able to look at things that are at the surface, that are in the sediment, that are at the banks, not and suspended like at the surface of the water column, not deep below. So there's also a problem there. Part of the reason again why we don't do this and look down is because again, it's costly, it's time consuming, it's really hard, it takes a lot of work. But again, it's still really, really important that we do this. So I would like to possibly use CHIRP. So as it was said before, CHIRP stands for compressed high intensity radar pulse. So unlike traditional sonar, which you guys are going to be seeing, your guys' left, yeah. Sonar, it would emit like one ping right into the water column, and it would only hear back stuff from that like one sound, like one frequency. Whereas CHIRP is going to continuously emit sound into the water column, and it's going to emit it over a long frequency, so along a larger range. So we're going to be able to get back clear images when comparing it to just traditional sonar. So Bohr et al. Was able to establish that CHIRP sonar technology has the potential to detect macroplastics in the water column. However, it had a lot of limitations to its study, right? They didn't look at raw data because they couldn't figure out how to get it off the CHIRP. So they were just analyzing these pictures here. So we actually contacted the company before, and they figured out a way to get that raw data off of the CHIRP. So that's one way that we could that we're going to work to try and fill this gap that they had. They also had some struggles with looking at trying to figure out if it was a bag, if it was a bottle. They had some trouble figuring out how the different orientation of the trash in the water column was affecting it, right? So think about it, if you have like a plastic bottle and it's this way, it's going to come back one way versus if it's horizontally, it's going to take up a different like space range in the picture that sonar is going to give them back. So we are going to possibly try to build off of this study while also connecting it all together to the bigger problem of microplastics. So my first research question is there a correlation between the amount of micro and macroplastic present in a cenote? I would also want to look at what is the accuracy and extent of which CHIRP technology can detect plastics in a cenote. So my objectives are to quantify the abundance of micro and macroplastics at different depths in cenote environments, to investigate a correlation between macro and microplastic in cenote environments, and to investigate the depth, accuracy, and types of macroplastics that CHIRP can identify throughout the water column in a cenote. For my study sites, I would ideally like to look at 3 different cenotes, one that is primarily used for tourism. So we know that macroplastics are going to be present, right? You're going to have a lot of people going out there. They're going to be drinking out of their water bottles. They're going to be having lunch. They're going to be using plastic utensils, things like that. However, because it is a tourism-based cenote, there's going to be more of this effort to pick up the area, to keep it clean, to make it look pretty, so that way you have more of those tourism efforts coming in, and you continue to have that revenue of tourism coming in and wanting to visit this place. Because if it's dirty, you're not going to want to go there, right? You're not going to get your pretty little tourist pictures to post all over Instagram and stuff like that. I would also like to look at a relatively clean cenote that has little to no visible macroplastics in and around the area. So a cenote that is a little bit more secluded, people don't really go to try to see what the quantity of macro and microplastics could possibly differ there. And then also looking at a dirty cenote, so one that isn't very well maintained, one that isn't very clean, with high levels of visible macroplastics to again look at the relationship between the micro and the macroplastics there. For the microplastic sampling, I would like to take 4 microplastic samples, one at the surface level, one at the mid depth, and one at the bottom depth of the cenote to look at throughout the water column. We'll also be taking a control sample at each location, and if time allows, doing a positive sample and a negative sample to test the DI water at the lab that will be used with these samples. And then the positive sample will be just to make sure that our technology and our methods are working the way that they should be. For the macroplastic samples, I would like to do traditional surface level surveys of the water and the surrounding area. So like I had mentioned before, that citizen science sheet that you have that you fill out to just kind of look around the area and see what you find, to use that to quantify the different types of macroplastics visible at the cenotes. I would like to use CHIRP to methodologically scan in a grid motion at the surface, the same way that Kat and Marisol had mentioned doing for their projects. And then I would also like to test CHIRP in a controlled environment to evaluate its effectiveness at detecting macroplastics and to see and analyze that data if there is a way to try to detect what type of plastic it is, to look at how deep it can actually detect the macroplastics, and to just overall build off of that previous study that I had mentioned. So I predict that cenotes with higher quantities of macroplastic will have higher quantities of microplastics present. I don't think that there will be any correlation with depth. So like, let's say there's more macroplastic at like the bottom of the cenote or like in the mid-level. I don't think that that's going to correlate depth-wise to the microplastic samples that are taken. I think that CHIRP will be able to identify macroplastics at all depths, but some beams will be better suited for the different depth ranges. So as again, Marisol mentioned, there's the different beams. So some are going to be better for looking at more like surface level macroplastics, and some are going to be better for looking at more deeper macro level or macroplastics. I do think that CHIRP will have some limitations when identifying types of plastic debris size and also be affected by environmental conditions. So if the cenote has more of that like overtop vegetation coverage and we're getting more of that like natural debris into the water column, I think it's going to have some difficulty detecting macroplastics versus natural debris in those environments. I also think it has the potential to be affected by things like turbidity, overall water quality, and temperature. Now, these are my resources. Thank you for listening to my proposal, and thank you to my mentors. Any questions? Okay, in the corner there, have any questions?
Are the smaller microplastics, like, are they able to sink, or are they dense enough to sink like down the water column, or would they just kind of still the surface?
So last year's REU actually looked at based off of density, and that one found that there were pretty much equally distributed throughout the water column just because of like mixing and stuff that goes on throughout the water column is what I think was causing it.
I mean, you said
Yeah.
but
So testing the DI water at the lab to see if there's already any pre-existing microplastics in their water, because obviously like they're really hard to filter out all the way. So that water that we're using to prepare our samples and clean our equipment could add and introduce extra microplastics into our samples. And then also just controlling for like environmental microplastics. So just taking like a container and pouring DI water into it to see what type of microplastics are present in and around the environment. And then the positive one would just be like, again, like I said, testing our methods. So adding a known amount of microplastics to a sample to make sure that the equipment and our methods are working properly. Explain it over again how you're using the different degrees on the curve to test how much macroplastics are in it. The macroplastic? Yeah. So basically, because the beams are like different widths, the narrow one is like obviously better suited. I believe that one was better suited for the surface level versus the wide beam was better suited for looking deeper. So looking at that, you're obviously going to get different types of pictures based off of what beam you're using. So using that to see how that affects the type of macroplastic, because obviously the plastic is going to have like different densities. So if you have like a plastic bag in the water column, it's going to deform a lot and it's going to be like constantly moving and shifting versus like if you have like your Starbucks cup, like that's going to be hard and solid. So trying to see which beam is better for detecting like which types of like macroplastics and seeing if there's any difference in that at all. And do you have like a that in mind to change the beam? I don't right now. Just because, like I said, this is like building off of like only one other study that had done this. So I think it's best to like just test a range of everything to get a better idea of what actually works and what doesn't. Good question.
Yeah, that's great. I was just curious for your method, in the cenote that has a lot of trash.
Mhm.
Do you plan on like taking a raft over there to, you know, be something? plastics in it for, I don't know. But do you plan on like using it after?
I haven't thought about that much just because I don't have my exact study sites because a lot of this is gonna be fluid and changing just based off of what we have access to and like what you guys are doing. So if you're going to one that is kind of dirty, like taking advantage of that and seeing what the type of access points could be. And obviously like keeping in mind like my health and like everyone else's health and just making that decision based off of like once we're there and how comfortable we feel and stuff like that.
Thank you very much. Next, I'm assuming it's one of the microplastic groups, yes, okay.
Hello everyone. My name is Jael Samama, and I'm a student. I'm a student here at NIU, and I'm majoring in water and soil science. So this whole REU is right up my alley. So for yes. So for my project, I will be looking at tying together geochemistry and microplastics in the Yucatan Peninsula aquifer. So a little bit of an introduction. Lorelei thankfully kind of introduced you guys to microplastics and what exactly those are and the role that they play in groundwater. So I will be explaining a little bit about major ions. So they generally work as an indicator of overall water quality. Usually groundwater has like a natural like amount of various major ions, but in higher concentrations they can pose a threat to not only human health, but also the health of the local ecosystem, like all the different plants and animals. Because as previously discussed, the Yucatan Peninsula aquifer is karstic. It is also very vulnerable to contamination due to the easy access to groundwater. A lot of these ions can be affected by anthropogenic activities. So, wastewater intrusion or discharge into groundwater can increase concentrations of various ions. And some of these ions tend to be things like sodium, magnesium, calcium, phosphate, sulfate, etc. So what exactly does this matter? Previous research has shown that microplastics can act as carriers for heavy metals, organic compounds, and various other things. Metal ions can absorb to microplastics and also promote the adsorption of single-stranded DNA onto microplastics, which can tie to one of our projects that we're doing for the REU. And unfortunately, no research has been conducted into the potential link between microplastics and major ions in the Yucatan Peninsula groundwater system. So I'm going to be looking into essentially linking the two. Some ions, major cations and ions that are present there are some of the previous ones that I said, as well as potassium, barium, and more. So my hypothesis is there a correlation between the concentration of microplastics and major ions in the Yucatan Peninsula freshwater system? I'm kind of basing my approach to this a little bit on Giselle Hernandez's research during last year's REU. Literally talked about it a little bit. She was investigating whether the concentration of microplastics can vary by depth in cenotes. And she found that at least above the halocline, they don't. So because of this, I'll be looking at a wider area, and I'll only be taking water samples from the surface as opposed to various depths. Some of my objectives are to assess the presence of microplastics in the Yucatan Peninsula aquifer and their effects on the local geochemistry. Also to quantify microplastic and water quality parameters collected at various points in the aquifer, which would be various different cenotes. And to evaluate potential effects of tourist activities on microplastic and ion concentrations. So kind of building off of Loreli's project. So I'll be using 3 different methods. Sorry, that one cut off at the bottom. I'll mostly be focusing on the bottom 2 that focus on the geochem. But to give you a little bit of more information on how the microplastics affect work as well, we'll be using the LDIR, laser direct infrared imaging system that consists of quite a bit of lab prep where we'll be doing some pre-filtration with a 10 micrometer metal filter, digesting the with hydrogen 30% hydrogen peroxide to get rid of any like organic compounds in the water, filtering again, and then doing density separation with zinc chloride, and then finally filtering onto a gold filter, which will then be inserted into the LDIR. And the results that this machine gives are the type of plastic, the amount of that certain type of plastic, as well as the relative abundance or just percentage of the total sample that specific kind of plastic is. And then specifically for the geochemistry, I'll be using 2 different machines. In the field, I'll be using the exact micro 20 photometer, which entails, I would add my water sample and use various different strips that test for different parameters to kind of see the concentration. And then in the lab, I will be using an ion chromatograph and injecting my samples into there to also detect various different ions. So my predicted results, not expected results, are that there will be a correlation between the concentration of microplastics and major ions in the Yucatan Peninsula freshwater system. Potentially, or particular types of microplastics may correlate with specific major ion concentrations, which I think might be the next slide, could potentially be a new area of research. Yes. So I'm a student here at NIU, and I will continue to have access to things like the LDIR and the ion chromatograph. So I could potentially further look into a potential of the adsorption and absorption of major ions onto microplastics, as well as some sort of correlation between the types of plastics and major ions to see if maybe different types of plastics tend to attract different ions or greater amounts of major ions. My source. And thank you. Any questions?
I have a very bio background, but I just wanted to know what role that gold filtration played, like you in your method slide, and like filtration. Can you explain?
So if I recall correctly from what Dr. had explained, in different labs, they will use different materials, but we use specifically gold because it's highly reflective, right? So you can just see them a lot better.
I'll be able to help out and see these things during the time, so, yeah.
You had a question yesterday that other people might benefit from hearing of it was one of you two. Somebody asked the difference between adsorption and absorption, which some of you might not know.
Great question.
Yes, what is the difference?
Absorption, because
Yes.
we're combining this.
Yes. So adsorption is for example, with the microplastics and ions, if the microplastics adsorb the ions, that means they kind of cling to the surface. And then, or like attach. And then absorption would be like a sponge, they kind of take it in.
We use the word absorption. The type of process. And we're not gonna distinguish. Right, you're going to distinguish between either one of those?
Or not.
So we're just gonna say
Yeah,
absorption, it's either effect, yes. Maybe ways in the future. we can tell. Right now, it's just. Absorption. Weird word, another weird word that you guys learn, like bathymetry, distortion, you know, you guys are all learning. Yeah,
Another question?
okay, great, thank you. Okay, yeah.
All right, my name is Valentina Mendes, and my project proposal is for the occurrence of tire wear particles in some places of the Yucatan Peninsula. So an outline, so I'll have a brief introduction and background on like tire wear particles, identify the research gap and the question that I had to I do not what is it? Sorry, I'm using my English to address the gap. And then my objectives, hypothesis, methods, as well as limitations and expected results. Okay. So first, we've already kind of discussed what microplastics are, so I'll go into tire particles specifically. So those are produced by the degradation of the tire, and that it's like through friction, and that includes rubber, heavy metals, and other things. I will be focusing on rubber specifically. And so with these tire particles, that we are concerned about like the toxicity to freshwater systems. And then this image kind of shows like, degradation through friction, that gets into the runoff into the freshwater systems like our cenotes. So we've already also discussed kind of like the hydrogeology of the Yucatan Peninsula. So it is a karst system. The cenotes of sinkholes that are connected through different like large distances and are vulnerable to surface derived contamination, which is what we're going to be examining. So previous studies have confirmed the presence of microplastics in the cenotes of the Yucatan Peninsula, but there is a lack of data on the specific contribution of tyroplastics and the role of like traffic density. So my study will address the gap by focusing on tire contamination, specifically rubber contamination in cenotes that are near roads. So that's the special attention to the traffic activity in accordance with like road proximity. So my research question is, how does traffic density influence the concentration of tire particles in the cenotes of the Yucatan? The overall objective of the study is to determine the presence and the distribution of tire particles in cenotes. And then under that, we will be identifying, quantifying tire particles in the water and sediment samples that we'll collect from cenotes. We will compare the levels between cenotes and areas that are in urban areas and close to roads, and then evaluate spatial patterns of tire particle concentration in relation to the geographic location of the cenotes, and then analyze the relationship between vehicular traffic frequency, so that's cars and buses, in the surrounding areas, and the tire particle concentration in cenotes. So my hypothesis is that cenotes located near roads or urbanized areas will have a higher concentration of tire particles, and then those that are in rural or more protected areas. So first and prior methods is the selection cenotes. We don't have the specific ones selected right now. We'll have to examine like the proximity to roads, the urban area, and what we have access to be able to select the cenotes we'll be studying. When we have those selected, the sampling will include both water and dust sampling. So water, just surface water in the cenotes, but then also sampling dust from the road that is near that cenote, so we can compare the composition of tire particles in the cenote and then from the road specifically. We will be quantifying vehicle traffic on the roads near cenotes. So it's important to know this cenote might be near a road, but this road might not be used very often compared to maybe a road that is used very often. There's a cenote there. So we'll be taking like surveys of like how often this road is used and like what type of vehicles are there. So we kind of have an idea and we're able to know that information as we're examining these cenotes. And then we will extract and analyze tire particles. We've already kind of discussed the methods for that. The prefiltration, digestion, density separation, and the final gold filter. And then to analyze this, we're using the LDIR spectroscopy. So that's an image of the LDIR there. And then the analysis can be done with like ANOVA and other kind of tests to know like the correlation and relationships between the different samplings that we have. And then some limitations here, just because of the short period of time that we'll be sampling, we'll be missing any kind of like temporal relationships, like any seasonal changes, if there's storms or anything that can mess with the runoff or the mixing that's going on within the water. So just to acknowledge that. And then we do expect that there will be higher concentration of thyroid particles in some of these that are in urbanized areas and near busy roads. We're expecting a positive correlation between the number of cars and buses that are traveling on these roads, and then the concentration of the particles that are in the sediment as well as the water. And then spatial distributions that will affect the potential entry routes for contamination into the underground aquatic systems. And then just kind of see the bigger picture, this research will contribute to the growing literature on microplastics and freshwater systems. And then there is a novel focus on the karst and road-based transportation of spreading thyroid particles. And then by connecting kind of the traffic activity to contamination and the ecotension of this, the project will support environmental monitoring and sustainable infrastructure planning. So kind of like that forward view there. Okay, thank you.
Any questions? Oh, we have over here. Hello. Yes, you mentioned that we put in
Mhm, mhm.
and
The water. We just so just seeing the composition, like the presence of the rubber particles, if they are the same that we're finding in the water. So that's what we expect to see. So just to compare those two. Yeah, so we have to know the traffic density. So to know like what is the traffic activity that is on the roads. Like there's a difference between there might be a cenote near a road that's not used very often at all. But if we're in an urban area where this route is used every single day, all day, then there has to be a difference between, or we're expecting to see a difference between those two cenotes. So just to have that number in mind to explain any differences you see in the water and the thyroid particles between those two. The effect of different rush hours, for example, causing different roads in one day. Yeah, that's definitely something to take into account. I think that would be something we'll discuss more with our mentor, Dr. Hiderato, when we're at CC. That has a better idea of the area and how we can make sure, like again, that's on also like a temporal thing that might be like not long term, but temporal within the day to know like different times. So I think we'll have to look into more to see. Maybe we'll be testing the same hour of the day at the same cenotes or the busiest time of the day for those ones, but we'll have to see that. But yeah, thank you. It's the same kind of process. We're going to be using LDI. It's just a little different. It's not water. It's less. Yeah.
Use a flashlight.
Mhm. Yeah. Mhm.
No? Okay, thank you. Lead us into. Oh, no. Just the tire wear particle, the tire wear particle. And then we will do the. Primary logic.
Cool. Hello, everyone. My name is Austin, and today or during this research, I'm going to be investigating 6 PPDQ and heavy metals in the Yucatan cenotes from the tire wear particles. And I'd like to thank Dr. Linchevsky and Dr. Tucker for helping me out throughout this. So first we have our significance and our areas of concern for our contamination. And then we just have the local population as main people for concern, the aquatic life, and then everyone else that this will affect eventually as this study continues to grow. So as these tire particles are entering our atmosphere, we'll begin to see the adverse effects that this has on the environment. And we can also see in a recent study what it's done to the coho salmon and how it directly affects them. And it can also affect us as health issues can arise with cardiovascular disorders, neuronal damage, and even risk of cancer. And these are just some pictures of, this is one of the cenotes from a blog, travel blog, and then that was just a picture of like the United States showing how everyone's going to be connected by these tire particles and the contaminants. And then here is what the actual chemical is. It's 6-PPD. So this is it. And this is what they place on the tires to stop it from degrading so fast. It's like a type of thing. And then here is what 6-PPDQ is. It's just with the addition of oxygen to that chemical. So just that addition of oxygen makes it contaminant and deadly to some of these species. And I will go over this log KOW value. Because it's greater than 1, that means it's more soluble in octanol than in water, which means that it's harder for this substance to travel through the water table, and it's gonna just like cling to your biology and like your other life forms in there, or it's more attracted to the organic matter that's in the water. So it's going to be harder to go through the water table. And then same with 6-PPDQ, it's greater than 1. So it's more soluble in than water. Then here's that process. So as 6-PPD interacts with the ozone or oxygen in the atmosphere, it's going to go through other metastable oxidation products, and then it will eventually be 6-PPD in the end, which is the contaminant. And then here is a little demonstration of the tire and road wear particles and how they interact. So we're basically never going to find road wear particles or tire wear particles solely by themselves. They're always going to be combined. So that's why I just refer to them in this the rest of the presentation as tire, road, and contact particles. And so that's just from the brake pad, it's from the tire, and it's also from the road sediment. And we're just gonna, for this study, we're just gonna put that all together because it's all gonna go into the aquifer system. And the heavy metals that we found from a study that was found, they just did the actual tire particles and not the reactant yet. So in the actual tire particle, it is aluminum, vanadium, manganese, iron, zinc, titanium, chromium, nickel, all these. This, you guys know these elements. And then heavy metals found specifically in the reactates, where the high concentrations of zinc, strontium, manganese, and barium. And this study here shows the concentrations that you have within the tire particle on that left one, and then this is in the reactant, so this is in the water sample. And as you can see, the zinc and the barium and manganese and strontium down there all have very high levels in their reactate, so it's still very
Pronounce-
leach. Okay, thank you.
I was like.
Leach. Okay. Leach. And then here are our cenotes. This is still to be determined, but right now we have LL, Verde Lucero, and then a wastewater plant, and then we have the P52 well, Domo, and these three, and then or these two, and then I just wanted to find one more ice-related cenote, so I just threw this on there. I don't know if we can go with that one. Yeah, but, so yeah, we just have ours going from the closest proximity to the main road and then more isolated to test for the concentration. So my research questions are, what is the concentration of 6-ppdq when comparing sites that are in close proximity to main roads compared to more isolated ones? And then the same question I have for that for the heavy metals. And then for my question 3 I have, is there a correlation between the 6-ppdq concentration and heavy metal concentration that we are finding so that we can confirm that these heavy metals are from the tire wear particles? And then question 4 is, I kind of like what Valentino was talking about, where you're, instead of analyzing the hotel option to do the traffic density during the times, if we can find that. So I might change that to that, but right now I have, is there a correlation between hotel occupants and the 6-ppdq in these cenotes? So it is more increase the concentration. So for methods, we just have the sample collection and then for both of them. But for 6-ppdq, we're going to do solid phase extraction, filtration, and then HPLC. With tandem mass spectrometry. And then for the heavy metals, we're going to use ICP-MS, which is inductively coupled plasma mass spectrometry. And here's the sample collection. This is just some of the techniques we can use. You can use the pull sample. This is the tremor, water sampler, grab sample, and then this is what we're going to be storing it in. It could be in an amber, it says to do it in an amber glass, but you can also do it in the PP, I forgot what it's called, propylene, polypropylene. Yeah. And then here are the methods for my 6-ppdq analysis. We have the filtration, solid phase extraction, your HPLC, and then coupled with the tandem mass spectrometry. And then here is a little example of what's going on during solid phase extraction. So in solid phase of extraction, we're first going to condition this cartridge, and we'll condition it with acetonitrile, and then we're going to have to fibrillate it at the end with like some water just to make it so it's not shocked by our sample. And then after we run our sample through, this material that's in there in the sorbent bed is going to stick to the 6-ppdq, so it'll just be like a sticky substance. Basically, is what happens. It's going to stick to each other. Well, it lets the other materials pass through, and then we rinse it and begin the elution process where we can finally get our final volume in a small volume with the compound that we want. And then here's a little demonstration of HPLC. I'm not going to go into it too depth because I'm not too sure about it yet. I just know like the basics. But this is a little diagram of what's going on. So, I mean, I can go. You want me to go over it? Yeah. Okay. Yeah, but that's what's going to happen. The little diagram. And then here's what's happening in the tandem mass spectrometer. Leave that up there for a sec if you want to look. And then here's the instrument that we'll be using. This is in the Tucker Research Lab at SNIUE. So he'll be showing us what's going on with that, and we'll hopefully get to help a little bit and walk around. And then here is what's also going on inside these. These have a triple quadruple. So this is another diagram of just what's going on inside the analysis. And then for the heavy metals, it's going to be similarly the same for the sample collection. But instead of for this, we have the sample prep where we're just going to put it in the 15 ml centrifuge, and where we can store this with 1.5 ml of nitric acid. And this can be stored for a while. And then we're going to use the ICP-MS system. This is what's kind of going on in that. And then acknowledgements, architecture, the research lab, FC menu, references. Thank you. Any questions?
Go on from there. Okay, now we can do last week.
Great. Hello, everybody. Welcome. My name is Daniela Sosa Ferreira, and I am a mathematics and biology student. And this is,
I'm Josue Rodriguez. I'm a biochem major.
and today we will be presenting our work in water microbiology and water chemistry as well, with the mentorship of Dr. Lipetsky, Dr. Singh, and Dr. Tucker.
Okay, so this is kind of just a little introduction as to what we're going to be looking at, what we're going to be doing. So first, what's an antibiotic? I'm sure you guys know an antibiotic is medicine that was created, drugs to fight against bacterial infections that we have. But with these things pop up like antibiotic resistant genes, this is basically a mutation in the DNA of bacteria that makes them resistant towards the drugs that we've produced for those viruses. They gain these mutations basically with evolution. It's bacteria dies off whenever we do take these pills, but then there are certain ones that are resistant to that bacteria and they have that resistant gene. So those are the ones that survive and they multiply basically through binary fusion. It also happens through conjugation, which they exchange DNA through a pili, and it makes other bacteria resistant to this. So that's why pollution is kind of bad. It promotes this process of happening. And with antibiotics, there are two general different types. There's the bactericidal and the bacteriostatic antibiotics. The bactericidal basically just focuses on killing the bacteria, and the bacteriostatic prevents the bacteria from growing their cell wall and prevents them from multiplying through binary fusion.
One of the most prominent health concerns of our time. And antibiotics resistance are not only prominent in hospitals, but they can also be present in the environment and spread through the aquatic system. This is why we're doing what we're doing. So environmental reservoirs, water can be become and act as not only reservoirs, but also as channels and spreading these antibiotics gene and bacteria in the area. And this is especially true in areas like the Yucatan Peninsula that have a karst aquifer system, and a lot of wastewater is able to then quickly seep into the groundwater, affecting the population and their health. And moreover, this is one of the first studies that is done comparing the different antibiotic resistance genes in a variety of aquatic systems, not only specifically cenotes.
All right, so the sampling design. So we decided that we were gonna go to a brackish lagoon, which is protected. So we were thinking of making this our negative sample, seeing how much antibiotics and antibiotics resistant genes we could find in this. This one there is some salt in it, so we're gonna work with that. Then we're gonna go to two cenotes. One's gonna be with high tourists population and then low tourist population. And then lastly, we're gonna be going to the wastewater treatment plant over there in Cancun. This will be our positive sample. Here, obviously, it's wastewater coming in, so it's like the first basically water that hits the whole system in Yucatan. So we're expecting to find the most antibiotic resistant genes there and the antibiotics present in the water.
So firstly, my project will focus on the detection of the REUs in aquatic system with varying human and environmental inputs. So my research question is, how does the presence of antibiotic resistance gene vary among aquatic systems with different degrees of human activity and environmental conditions in the Yucatan Peninsula? And the hypothesis proposed is that aquatic environments with higher urban
impact, particularly wastewater, will contain a higher diversity and abundance of these ARD compared to lower impact, such as a protected lagoon. And some rationale for this hypothesis is we have found a couple of studies that have studied similar topics before. For example, Congreve et al. In 2008 that found class 1 integron, a high level of calcium integrons, which is a strong, correlates strongly with the presence of ARGs in wastewater impacted environments using quantitative PCR. This suggests that a high urban impact will affect the quantity of bacteria and bacteria with those genes. Moreover, in 2011, in REU, the LOT started out found that pharmaceutical contaminants and bacterial pathogens in groundwater were very abundant. This is important because it's specifically focused on where we're going to do our research. And this can also lead to the conclusion that higher human impact can affect the presence of these ARPs. More recently, Alexia Galera et al. In 2023 found that sayotes used for tourism had high levels of contamination. This again is very relevant to our experiment since we will be testing in sayotes for contamination. And Lee et al. In 2020 showed that even treated wastewater retains a considerable load of ARGs. That means that that underscores how difficult it is to rid water from these bacteria that are resistant to antibiotics despite efforts of treatment. So what are our objectives? First, we will try to detect 8 different genes linked to antibiotic resistance in 4 separate environments. We will compare this environment, like we mentioned, the wastewater, the lagoon, and the two samples. And finally, we'll assess correlations between these antibiotic resistance genes and the anthropogenic and physiochemical factors such as salinity. The way we will do this first is through sample block. So we will do 3 steps. First is the 3-step filtration, and then the DNA extraction with the kit that we have. It's a commercial kit called DNA. And finally, we will be able to store them at -20 degrees for later PCR analysis. Moreover, for molecular detection, we will use, for those unfamiliar with PCR stands for preliminary chain reaction, and the main goal is to exponentially amplify a specific region of DNA. This is useful for us because we are trying to target genes which are specific regions of DNA, but specifically that we know specifically associate with mechanisms that allow bacteria to resist antibiotics. 1. So we will use 8 primary pairs for our target genes and around 25 to 35 samples, which is common practice. And we use tech polymerase enzymes to extend them at 72 degrees Celsius. Moreover, once the genes are amplified, meaning once we have a higher quantity of these target genes that we're looking for, we will be able to visualize them using gel electrophoresis. The point of gel electrophoresis is to separate these genes that we have amplified by length. They are varying base pairs, which means varying nucleotides. So the DNAs are going to be, some are going to be larger than others. In this way, we'll be able to compare and specifically determine the specific DNA that we have found to the known antibiotic resistance. These are some of the genes, these are all the genes that we're testing actually. Firstly, the class 1 integrons will serve as our internal control. It is a multiple element marker. Like I mentioned before, this class 1 integron correlates strongly with antibiotic resistance genes, meaning that if we're able to detect the INTI1 gene, most likely there are going to be antibiotic resistance genes in that sample. Then these other genes correspond to different classes of antibiotics. So beta lactams are going to be genes, moleculase, A, glycoside, ACA, and transacine, A, and W. Moreover, these are the different fragment size. As I mentioned, the levels of DNA are going to be what we will use to identify them in the gel electrophoresis and the amino temperatures. This means that the PCR procedures are going to be different for each gene, and we will have to perform multiple different separate rounds of PCR to be able to correctly quantify expected results. So we expect, based on previous hypotheses and work, that the wastewater treatment on positive control will have the highest detection of multiple ARPs. Moreover, the cenotes will be in a moderate level with the higher populated cenotes displaying higher quantities of ARGs as compared to the low tourist infected cenotes. And finally, the lagoon will show low to no detection of ARGs as predicted, and it would have a new fishery baseline. Hopefully, our findings will shed light on the effects, the anthropogenic effects, and the environmental effects of water on the bacteria. Again, the salinity is also important because it varies among these three aquatic environments, and salinity could correlate with the ability of bacteria to survive in these environments, such as some future directions. So what could we improve? Maybe if we had a little bit more time. What is next after research? Firstly, qPCR to quantify the copy numbers. So I explained what PCR was. qPCR not only will help us identify specific genes, it will help us identify the abundance, the amount of genes found in separate different environments. So this can be very helpful to identify specifically what antibiotics perhaps are most common and what we should be worried about. Moreover, 16S RNA sequencing. 16S is going to be a very common gene found in multiple bacteria. When we do DNA sequencing for this gene, we will be able to identify proportions of microbial. We will be able to identify if maybe E. coli is more prominent in certain waters, or in certain waters like wastewater treatment, because it's a gut bacteria, or if maybe lagoons have other non-pathogenic bacteria. We'll be able to identify what bacteria we're looking at. Moreover, seasonal is very important. If we're able to sample across tourism periods and seasons of high population versus low population, maybe this will shed light on on if the anthropologic effect is actually valid or not, and then assess correlations through statistical analysis of all of these things will be very important in the bigger picture of antibiotic resistance genes that will help us fight this terrible.
Okay, so now I'm going to be looking at my study. I'm focusing more on the antibiotics and the organic chemicals that are found in it. So the antibiotic pollution in the freshwater systems of the Yucatan Peninsula. So these are my research questions. How does antibiotic concentration change across Yucatan's water systems when testing sites with high to low tourism? Is there a different concentration of specific antibiotics at sites with change in human activity? And then does the concentration of people in the water system affect the concentration of antibiotics, and which specific ones are found in it? And then the last one is to correlate mine and Danielle's projects. Does the presence of specific antibiotics in sampled waters correlate with the presence of the specific antibiotic resistant genes that they found? This is my hypothesis. The concentration and diversity of antibiotic pollution in the freshwater system will be significantly higher at locations where there is more human activity compared to areas where there is little to no human activity. So these are the antibiotics that I'm going to be looking at. As you could see, the classes match up with the ARG. So there's your tetracyclines, the beta-lactams, and the macrolides. So the tetracycline in itself is actually antibiotic as well. So what makes this a tetracycline is these four hexene rings interconnected together. Then for the ampicillin, it's a beta-lactam. As you can see here, this functional group right here is what makes it a beta-lactam. Then we have the clarithromycin. Then we have the penicillin G. The penicillin G was actually, we had created the penicillin drug, but we actually became resistant to some of those as well. So we had to like develop different ways to fight these bacteria, which is crazy how we're already like trying to create new antibiotics compared to the old ones so that they're effective. And then we have the azithromycin, it's another macrolide. And then these are all the polarities right there. You'll see how they come into play later. So these are the general use. The tetracycline, the use for these, it treats many bacterial infections, including UTIs, STIs, pneumonia, and respiratory tract infections. The ampicillin, also many bacteria infections, including meningitis and UTIs. Penicillin G is the streptococcal infections, pneumonia, syphilis, meningitis, and anthrax. Methicillin focuses on Staphylococcus aureus bacteria. Azithromycin focuses on respiratory tract infections, skin infections, STIs, and ear infections. And then the clarithromycin focuses on respiratory tract infections, skin infections, STI, and ear infections as well. So methods. We're gonna be collecting the water samples in the amber glasses, as mentioned earlier in Austin's presentation. We're gonna be doing 3-step filtration, the solid phase extraction, liquid chromatography, and mass spectrometry. So with the 3-step filtration, the way I'm gonna be using it is to filter all the biomass that we need for the microbiome study. But what I'm looking for is more of that filtered water. That's where all of the antibiotics that I'm looking for are going to be in. We're going to do SPE, same thing there. So we're going to condition the cartridge with methane. It's a strong organic solvent. This is to saturate the solvent bed and to activate it. Then we're gonna dilute it with some water so that the methane isn't in there. And then we're gonna finally add the sample. Since these are polar and the sorbent bed is non-polar, it's gonna like stay in there, and then we're gonna add another organic compound so that it can move through that mobile phase. Sorry, through the stationary phase. With this, it also kind of works the same with liquid chromatography. We're gonna have a solvent there. That's gonna be our mobile phase. It's gonna go through a pump, and then we're gonna inject the water sample in there. It's gonna go through the HPLC column. This is the stationary phase. This is usually filled with silica. So our antibiotics are gonna be stuck in there when we put it in with the injector. And once we add the solvent, they'll move through the column. Through here, we're seeing the difference in movement. So with polarity, some chemical compounds move at different speeds, and that's what we're going to be looking at. That's what's going to help us identify, see what we actually have in there, and find what we're looking for. Then we're going to move it on to mass spectrometry as well. It's in conjunction. So with mass spectrometry, we need to put in vapor of the water samples that we have. This helps vaporize it. And then an electron beam is shot at it so that we could ionize these molecules. And with ionized molecules, it helps because we could accelerate them. This is going to be done through the magnet. So the magnet's going to push them towards the detector. And different molecules, chemical compounds land at different places. So some are bigger than others. So as you can see in the detector, it hits it at certain spots. So this also helps us quantify and see which antibiotics we actually have in there and if they're the ones that we're looking for. So the expected results, there should be higher antibiotic concentrations at sample size locations as sample size locations increase in human activity. More classes of antibiotics should be detected in high tourist areas, and the density of people in certain areas should affect the different antibiotics found. We should also be able to correlate most of the antibiotics found in my study to Daniel's study with the ARGs. And then limitations. Obviously, there's the time restraint. We only had about a week to fully immerse ourselves in this topic and try to gather up all the facts. Over there, we only have 3 weeks, and we're all going to be helping each other. So we're not going to be able to fully focus on one study. And then the detection limitations, we only have certain reagents to find certain antibiotics. There might be more antibiotics in the water sample. So if we were to have all the other reagents, we'd be able to see a bigger picture and see if there is more other types of antibiotics found in the water.
And finally, why are we doing this? What is the significance of our project? Firstly, ARG surveillance. It is very important because this is one of the first comparative molecular researches done in the region. So this could shed light really to what's going on and maybe protect some public health. Speaking of public health, this can support the area by identifying the environmental ARG hotspots. This way, people would know what to avoid, where to be careful, and just keep safe overall. Moreover, water quality. Hopefully, if our results are conclusive, we will be able to improve water waste treatment and perhaps influence certain policies in Yucatan to be able to improve life for everybody in the area. And finally, sustainable tourism is very important since it will be able to inform tourists when to go, where to go, and protect the health of both native people and tourists alike.
And then these are our acknowledgements. We'd like to thank all our mentors for helping us through the process of learning all these new techniques and finding all the papers online. To Marsha and Paula for being very patient with us in the lab. And then all the NIU, REU, and CC staff that we are going to meet through this whole process. And then these are our references. And thank you.
Thank you.
Any questions? On the antibiotic?
Yeah. Oh, one of the first specifically to compare antibiotic resistance genes in different aquatic environments, such as brackish water, the lagoon, as well as cenotes, as well as the waste treatment.
I saw.
It's going to be microbial contamination. So it shows that there's microbial contamination with correlated with the amount of tourists. However, we're looking for the exact antibiotic resistance genes. There might be more microbes, more bacteria, but we're testing specifically the genes in the whole bacterial population.
Okay, not hearing anything. Thank you.
Great job, guys.
Thank you. Thank you.
Stop recording and stop sharing. And then before we go anywhere, let me stop sharing. And then I think this is it. Stop recording. Stop. Okay.